This video is part of CAE Associates ANSYS e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an ANSYS channel partner since 1985 and have developed our ANSYS e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of ANSYS courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
We're here talking about checking your FEA results, and obviously any validation and verification of any finite element analysis is an extremely important step. Just because you were able to get a solution of your model doesn't mean that it's correct. A thorough review of all the results and all the inputs into a finite element analysis is a must for any analyst doing finite element analysis. The first thing you should realize is that, of course, that finite element analysis in general is an approximation. We are making engineering assumptions when we do finite element analysis. We're approximating things not only at the mesh level, we're approximating a continuous system as a finite number of elements, but in general, any analysis that you do could really be a 3D coupled field, electromagnetic, CFD, thermal, structural, of an entire product and its surrounding domain, but we use engineering judgment and reduce that model down to something that's more manageable. We'll do a structural 2D axisymmetric problem where loads and boundary conditions come from other domains that were solved separately. All of these engineering assumptions have to be understood. They're all going to contribute to the accuracy of your final results. In addition, we obviously need to understand all the input and check all the inputs to a finite element analysis. No amount of mesh refinement is going to help correct for bad inputs. We need to check things like geometry. Do we using the correct units? We're using nominal dimensions. Should we be using minimum or maximum dimensions somewhere? What about defeaturing? We remove features from any geometry. All of that's going to contribute to the accuracy of our end result. Material properties, we want to make sure that we have the right materials assigned. Are the materials nonlinear? Do we expect plasticity in there anywhere? Material properties, are we using, again, minimum values or nominal values or approximations in there? Obviously, loads and boundary conditions. Do we have the right units, the right directions? Are we under or over constraining our model? And simply understanding what loads and boundary conditions mean, what it means when we apply a point load, what it means when we fix a boundary. Because in finite element analysis, a boundary is fixed, it can't move at all, but that's pretty hard to do in reality. There's always some flexibility in any support you have. Contact and connections all have to be checked. Are the parts properly connected? Am I using the right type of contact? Frictional contact or bonded contact. The contact stiffness also plays a role in the accuracy of the model. And then, of course, the analysis settings, the time steps. Do I have large deflections turned on? Convergence criteria. What element types am I using? What options am I using for those element types? All these things are things that need to be reviewed. This is not something that's going to happen, obviously, automatically. This is all required engineering judgment for you to review your model, make sure that all of your inputs are correct to that model. Also, almost any of these things, as far as inputs, there's a potential variation in them. We talked about, nominal dimensions, nominal material properties, but really there's a variation. And you should assess that as well. That's actually a different e-learning webinar that we had on parametric analysis, and you can actually find that on our website if you're interested in reviewing that. Learn how to vary things parametrically in Workbench and do a sensitivity study. So once this is all taken care of, you reviewed all this, then we can go in and try to assess whether our quality of our mesh is adequate for the problem that we're doing. Obviously, adequate mesh discretization is important in all critical features. We want to make sure we have enough elements through the thickness. We want to make sure we have enough elements around a fillet or curve. And we want to also make sure that those elements are of reasonable quality. When you use Workbench, it generates a mesh. It has a less aggressive mesh quality checks than MAPDL has, for those of you who used to use classic ANSYS. But Workbench offers a mesh metrics tool that will let you review all of the quality measures before doing a solution. If you've noticed when you've used Workbench that it never generates warning elements. If you used ANSYS MAPDL, you'll find that you get many elements that generate warnings and possibly elements that generate errors. Well, Workbench, it either creates a mesh, which means there were no mesh errors, or it doesn't create a mesh, which means the elements failed their quality checks. I'd like to do a quick poll and find out if anyone here is actually using the mesh metrics tool. That's what we're going to talk about here. So Christine is going to set up a poll and invite you all to submit an answer to that, and we'll look at those answers a little later. So the mesh metrics tool allows you to review all the different mesh quality measures of the generated mesh before solving. You don't want to submit off a run and find out that your mesh had pretty poor elements in a critical region and then have to change the mesh and rerun it. We can also use this tool as a way to actually see the different element types that are in the model. Different 3D model, you might have tets and bricks and pyramids, etc., and you want to look at them separately. We can do that using this mesh metrics tool as well. Things that are available are element quality, a general measure that is a measure of the ratio of the element volume to the average element edge length cubed. Aspect ratio, size of an element to its length, Jacobian ratio, warping factor, parallel deviation, maximum corner angle, skewness, and orthogonal quality. Of all these measures that are available in the mesh metrics, only the two starred ones, element quality and Jacobian ratio, are actually used by the mesher to check whether the mesh is acceptable or not. So the only shape checking that's done by the mesher is if you use standard mechanical, it checks the Jacobian ratio at the integration points, make sure that it is less than 40. It checks the element quality and make sure that it's greater than 10 e to the minus 4. And of course, it makes sure that all the elements have greater than 0 volume. If you set your mesh checking level to aggressive mechanical, we look for, again, Jacobian ratio greater than 40, but computed at the nodal points. I'm sorry, less than 40. Greater than 40 would be an error. Element quality greater than 10 e to the minus 2, and element volume has to be greater than 0. So what I'd like to do now is bring up Workbench Mechanical, and let's take a look at how to use some of these mesh metric tools. Go and bring up this. All right. So here we have a mesh of this part, and if we click on mesh in the model tree, under the details of mesh at the bottom, we see statistics. Click on statistics. You may have seen this where it gives you the number of nodes and elements in the mesh, but there's also a mesh metric here. The default is none. It doesn't show you anything. But we can change that to any of those mesh quality measures. So the first one we look at, let's say element quality. And what that does is it brings up this bar chart down the bottom here that tells you the element quality value and the number of elements having basically that element quality. Now the first thing you'll notice here is that while this looks like a brick mesh, you'll see that I have tets, hex, wedge, and pyramid elements. That's because this was done using a hex-dominant meshing method. So one thing, the first thing, before I even start looking at element quality, I may want to assess how many of each different kind of element is in the model. And the way this is set up, that's kind of difficult. So I'll go to controls and say, instead of looking at 10 ranges, let's just make that one range. And now I can see that I have 111 TED elements in the model. I have 286 brick elements, 223 pyramid elements, and, oops, not clicking the right thing, we'll get 6 wedge elements. So this is a quick way to kind of take a look at the different types of elements in your model. You can see that this hex-dominant method, while it is, mostly bricks, it's not mostly bricks by a lot. There's 286 bricks and 223 pyramids. So let's look at some of the quality measures now. Go back to looking at 10 bars here, and we can see that the quality measures, if we click on the TETs, we can see there are some TETs that have a pretty low quality, 0.01, approximately 0.01. If we zoom in on those, obviously these are some pretty skewed and flattened out TETs. There are a few pyramid elements that also have a low quality there. So we can click on any of these bars at any point and look at the elements that meet that quality level. You can use this kind of to set your own warning limits and decide which elements are unacceptable in critical regions. We can look at other quality measures. We can look at aspect ratio. And you can see here, this is pretty skewed. Most of the elements have pretty good aspect ratios, but there's a few here that have pretty high aspect ratio. And it's pretty hard to see those bars. So what we can do, if you're using these mesh metrics on this graph, on your keyboard, if you hold down the Alt key and you can zoom in, you draw a box from left to right, we can zoom in on that little region and then get a better see which of these elements have really poor aspect ratio. So here we have one TED element that has an aspect ratio of about 250 and one pyramid element that has an aspect ratio that bad. To go back to the full view, I hold down Alt and I zoom the other way. I draw the box the other way. That snaps back to a full view. So that's how we can use this to assess the different levels. Jacobian ratio. You can see here again that most of my elements have a Jacobian ratio up here. But there's one element, if we zoom in here, that actually has a Jacobian ratio of -100. There's a TED element in there that has a Jacobian ratio of -100, and you may say, well, you would think that would be an error. Unfortunately, ANSYS doesn't flag that as an error because there are certain situations where a negative Jacobian ratio is expected, so it doesn't want to stop an analysis where you want that. So unfortunately, that doesn't come out as an error. So this is one of the things that's critical to check these things before we actually go and run a solution with that. Now, you may want to also look at the Jacobian ratios up here, but everything is kind of lumped together. And that's where these controls come in. Instead of having an x-axis that goes from -100 to 15, we can set it to go from 0 to 15, and we get a better view of what that looks like, what the distribution of the Jacobian ratio in the elements. So if I want to see the hex elements that have a Jacobian ratio of about 5, we can click that, and you can see that the model displays those hex elements that have a Jacobian ratio of 5. There's other measures in here. Parallel deviation. Notice parallel deviation is only a check done on hex, wedge, and pyramid elements. TED elements are not included there. The corner angle, maximum corner angle. Obviously, a corner angle of 180 degrees is basically an unsolvable element, and we're very close to that on some of these here. Skewness, similar type thing to angle and orthogonality. Quality, skewness and orthogonality are values that are generally used by CFD codes to do mesh checking. They are available, those same checks are available for mechanical codes for your review, but no mesh adjustment is done based on those. So obviously this is a pretty poor mesh based on our quality measures here. You know, I have poor Jacobian ratios. I have a lot of element qualities that are very low. And that's because we used a hex-dominant method, which looks nice on the surface, but as you get down into the model, we don't have such great elements. So let's see if we can improve this mesh. Let's go to a different method. We're actually going to use the multi-zone method, and I'm going to go ahead and suppress this sizing. And we'll regenerate a mesh here. Should only take a second. And this is using the multi-zone method. And one thing we immediately see is that we have all brick elements now. There are no tet or wedge or pyramid elements. And we can see that the element quality is much better, 0.7 up to 1 there. If we look at Jacobian ratio, you see our Jacobian ratio goes from about 1 to 2.7. The maximum values are actually displayed, min and max values are displayed in the details as well as we change that with the standard deviation from that as well. So you can see we obviously have much better quality elements in this model now. We've used a different mesh type. We got all brick. They're relatively good shaped bricks. If we look at maximum corner angle, maybe we have one or two that have a pretty high corner angle in there, but overall, generally good shaped elements. So that's how you should do mesh checking beforehand in Workbench. We should be using these tools to review our mesh because it does not give us the warnings and things like MAPDL would do. Let's go back now to our PowerPoint. And let's look at what we do after a solution to verify our results. So we've got a mesh, we've done some mesh checking beforehand, got it down to much better quality elements, and we're going to go and solve the problem. So even though you've done some thorough checking before the solution, you checked all your inputs, checked your mesh quality, doesn't mean that we're done. Obviously, once we generate results, we need to verify those results. This, obviously, just like the pre-solution checking, involves good engineering judgment. This is not something that's going to happen automatically for you. Each engineer needs to verify his or her own results. You should have expectations of what results you're expecting. You should have an idea of what stress levels are going to be in the model, what the maximum deformation should be. And anything that varies significantly from these expectations obviously should be investigated. Some general procedures for validating results. Number one, obviously check the displacement solution. Look at a deformed shape. Is the part deflecting in the direction you expected? Does it make sense based on the loading? Don't just look at the shape, obviously. We also want to look at the magnitudes. ANSYS Workbench will automatically scale displacements so that they are visible in the model. They look reasonable for the model, but the magnitudes may be way off. We should check our reaction forces using the probe tool. We can check reaction forces in a structural analysis, reaction heat flows in a thermal analysis. For a static or steady state model, those reaction forces should balance the applied loads. If you have weak springs active in your model, we want to make sure those weak springs are not taking any of the load. They're there just to hold the model in place to remove any rigid body motion, but not actually take any load. So we need to check the reaction forces going through those weak springs. And lastly, we want to obviously evaluate the mesh. Is the mesh sufficient to calculate the stresses or the results that we're looking at? So checking reaction forces can be done with a probe tool. A probe tool can be scoped to a boundary condition and get the reaction force going through that boundary condition, make sure that the total equals the applied loads. For weak springs, we can choose boundary condition. In the boundary condition, we choose a weak spring. It'll tell you the total load going through all the weak springs. These values should be very small compared to the applied load. Shouldn't be taking any significant portion of the load. Then we can use some tools in Workbench to evaluate whether our mesh is adequate or not. This is done by the fact that while displacements or degrees of freedom are calculated at each node in the model, stresses, strains, heat fluxes, etc. are what we call derived quantities. They are calculated on an element-by-element basis using the element shape functions and the values of the degree of freedom at each node. So each element will get a different stress value. Those stress values are extrapolated out to the nodes connected to that element. So at each node, each element connected to that node may report a different stress value. Workbench, by default, reports the average value of all the elements connected to a node. So this node here connected to two elements. The first element says the stress is 1,000. The second element says it's 1,200. When you look at the results in Workbench, you would see a value of 1,100 at that node. Now, anytime we do an averaging, obviously some value is going to, included in that averaging, is going to be higher than the average. That means we're always going to have a stress calculated to some element that was higher than the average value we're looking at in an element, at a node, sorry. If those values are significantly different, then we need to go back and judge whether we actually have a fine enough mesh in that region. So if we go in Workbench and we go under any display of stress or strain, we have a display option here. And the choices are unaveraged, average, nodal difference, nodal fraction, element difference, element fraction, or element mean. The default is averaged. So we are looking at, as I said, an average value at each node. That means somewhere, some value is actually higher than that. To get a better understanding, we should be reviewing not just the average results, but also the unaveraged results. When we do that, we may see something like these two elements disagree on the value at this node. The difference between them is 124 psi. That's 5.2% of the total stress. Now, is that an acceptable value? And this is something that I can't tell you. This is something that you have to use your engineering judgment to assess. If my stress was off by 5.2%, what does that mean for my results? What does that mean for my life calculations? What does that mean for any failure criteria I have, any stress limits that I have? Is a difference of 5.2% significant? We can also look at the unaveraged stress contours versus average stress contours. Difference there, 4.4%, again, do we need, is this a significant difference? That really depends on your situation, how much margin you have in your model. The other thing to be aware of is that in a continuous model, the average and unaveraged values really should be the same or very, very close. But there are certain things that will actually cause discontinuities, and no amount of mesh refinement is going to get you a continuous solution there. These are known as stress singularities. Something like a point load applied on a solid model is going to be a stress singularity. You can easily see that. If I have a load applied over a zero area, as the area goes to zero, the stress, which is the load divided by that area, goes to infinite. As I refine and refine the mesh, the area associated with this load goes down and down, the stress goes up and up. So I can never achieve a converged, mesh converged solution at this point. Same thing occurs in a sharp corner. The stress is going to be infinite in that sharp corner. If I refine and refine the mesh around that corner, I will find that the stress will go up and up. So how do we deal with this? Well, real structures do not contain stress singularities. They are a fiction that's created based on the modeling assumptions that we've done, the simplifying assumptions. I have simplified a loading to be acting at a point. It doesn't really occur like that in real life. There's no such thing as a point load or a load acting over zero area. So how do we deal with this? Well, if they're located far away from the region of interest, so I have a point load applied here, but my region of interest is down here, I can ignore the fact that I get this peak stress right under that point load and simply select just this region for evaluating the stresses, and then I can see that I actually get the correct max stress for that region. The problem occurs that if they are in a region of interest, if I have a singularity in the region of interest, I obviously need to take some corrective action. I need to change my model. I need to add a fillet or take my point load and distribute it out as a pressure over an area. So depending on what you're interested in, how you deal with singularities is going to depend on where that singularity occurs, whether it occurs near the region of interest or not. But let's go and take a look at how to look at some of those mesh discretization tools to check our model. So I'm going to go back to that model I had, and we're actually going to go ahead and solve this model. It's got some pressure load applied on it. It's got some supports. And we'll go in and see that this mesh, I'll pull this down a little bit, has, this mesh has generated a stress, and I have a max stress of 72.7 KSI in this region. Let's look at some of those other ways of looking at stress. So I'm going to take this, I'm going to duplicate that, and instead of looking at the average value, let's look at the unaveraged value. I'll evaluate that result. Now, when I take this mesh and I look at the unaveraged value, we'll see that my stress level is at 78 KSI compared to that 72 KSI for the unaveraged stress values. So this obviously is a stress that is not converged based on our mesh. We have a difference of about 6 KSI between the average and unaverage values out of, say, 77 or 80, so maybe 5 to 10% off. So even though our mesh here was reasonable, according to our element quality measures, it's not reasonable for extracting stress values. We have a mesh that was not fine enough to get good stress values, even though the quality was acceptable. So we would need to go in and, based on these error measures, refine our mesh and do some effort in there to get more elements around the fillet, and we would go and create a